First of all, I would like to thank especially Rogério, Marcos Maia for this beautiful meeting. It keeps alive the Professor Opher's goals and bringing together theoretical and experimental people from astrophysics, cosmology, gravitation is very good for us. It's very nice. Let's start with this afternoon session with Professor Júlio Fabris from Universidade Federal do Espírito Santo. He's going to talk about, let me see, a Newtonian theory with variable G. So, Júlio, please, you can start.
Okay, Vanessa. Então, inglês, né?
Yes.
Okay. So, thank you very much for the opportunity to speak here. I will talk about a work made in collaboration with some colleagues like Germán Lugones and Júnior Toniato and Professor Brasil that I will talk about in the end, about the formulation of a Newtonian theory of G variable, variable gravitational coupling. The motivation for this work, I think, I hope it will be clear during this seminar. So I will make it, the seminar is very simple, the ideas and many of the results. So I just revised some basic things. Wait a minute. Why it does not pass? Okay. That the Newtonian gravity it can be summarized by the Poisson equation that is written here, and it says that the Laplacian of the gravitational potential is equal to 4 pi g rho, where rho is the density, g is the gravitational coupling. And it's well known, even the fact that its versus square of the distance of a point mass is contained in this equation. The Poisson equation can be obtained from a Lagrangian formulation. We're writing equation 2, this Lagrange. It's not very complicated. The variation using the traditional Euler-Lagrange equation here in equation 4, we can obtain hence the Poisson equation. Okay, and we can apply this Newtonian gravity, of course, in many situations. Most of the situation apply, of course, the Newtonian gravity. When we drop something on the table, you are using the descriptions of this phenomenon is just using Newtonian gravity. When you study a satellite around the Earth, it's enough to use the Newtonian gravity. But also, beside that, we can describe more complex systems using Newtonian gravity. For example, we can construct a Newtonian cosmology. And it's very curious that the construction of the Newtonian cosmology arrived in the 30s, almost 100 years ago. And after the formulation of the relativistic theory of gravity, of the universe, after the formulation of a model for the universe in the general relativity. This is for many conceptual reasons mainly. But the Newtonian cosmology can be obtained from the continuity equation that's written here, from the Euler equation, that's also the second one that is transparent, and the Poisson equation. Hence, if you want to describe expanding universe, it's not very complicated. We can consider somehow the Hubble-Lemaitre law, writing the velocity field as a logarithm derivative of this function A, which we'll later identify as the scalar factor, multiplied by the distance of the object, the physical distance in this case. And insert this ansatz in the previous equation, can integrate the density, and it's very well known. You obtain this equation 9 that gives the acceleration uh, um, of the scalar factor, okay, the second derivative in terms of density with a minus sign. That is a consequence of the fact that gravity is attractive. And integrating this equation, since we know how whole the density behaves, we can obtain the freedom equation. This equation has a quite simple solution, and for what in relativist cosmology we identify as a flat universe, but here we talked about a universe with zero energy, since we are in a Newtonian context, we have this solution where the scalar factor scales at t to 2/3 power, and the whole decays as the second power of time. This, by chance, is the same solutions as you can obtain in relativist contexts for a meta-dominate area. And this is quite expected in some sense, since in the meta-dominate area, the pressure is zero. And in the sense, the Newtonian equations that do not fill directly the pressure in a homogeneous and isotropic context can reproduce these relativistic results. This is quite very well known. Now, in Newtonian theory, of course, that's one of the main conditions for the construction of the theory, the gravitational coupling is supposed to be constant. And the question is why, if there is any reason to consider that a gravitational coupling that does not vary with time, that varies with time or with the position somehow. We can think in a more general framework. And this has been first considered long time ago in the 30s, also almost at the same time that the Newtonian cosmology was formulated by an hypothesis of made by Dirac, okay, in an article in journal Nature, where he speculated the possibility of having a varying G. At that moment, Dirac has supposed some numerical coincidence involving big numbers. It's something that um, somehow you can think that's quite a kind of a numerology, but there is a sense to speculate about that. For example, you consider that this combination of the fundamental constant G, C, H bar, so something that involves gravity, relativistic theory, and quantum mechanics, involving also the Hubble parameter that seems cosmology in the sense, this combination gives the same value as the mass of the pion. At that moment, it was very important because the pion was considered as the particle that represents the nuclear force. And if you do not see this as a coincidence, but as a fundamental relation, there are Dirac speculate, make some speculation why we must consider this. And since age zero, that is connected with the age of the universe, the Hubble parameter, of course, varies with time. Some fundamental constant must also vary of time in order to keep this relation. And the hypothesis made by Dirac is that the gravitational coupling must vary in this case as the inverse of the time. Today, there are many constraints on the variation of the gravitational coupling. For example, to my knowledge, the last results obtained by some experiment indicate that if there is some variation of G, this must be at least of the order of 10 minus 13 per year. So it's a very slow variation that's allowed by observation of the experiment. Even though such variation may have some consequences in many moments in the history of the universe and also in many systems, like, for example, some stars, some in equilibrium stars, mainly, as we are going to see later, compact stars. So how to implement in a Newtonian context the variation of the gravitational coupling, if you want to implement this. And the reasons why you can think on the implementation of this variation, we'll discuss later. The point is that the first proposal in the sense was made in 1978 by McVitie, who took the equation, the Poisson equation, and just substitute where we have a constant g, the gravitational coupling, by a gravitational coupling that depends on time. So it's very simple proposal, but very limited in the sense that we cannot apply such possibility first to some static system, for example, a star, and also we do not have a dynamic equation to determine how G must vary with time. So we must suppose the variation of G. And McVitie has considered some possibility, mainly this possibility given by Dirac in the 30s, almost 40 years before. And he implemented this, and what he's found is some cosmological model, for example, that expands in a slowly rate. For example, in this case, the scalar factor does not evolve as with a power 2/3, but 1/3, typical of stiff matter in general relativistic context. So the expansion is very slow. Sorry. And what we want to do, the idea that we have tried many times ago is to try to construct a self-consistent theory, Newtonian theory, with a varying gravitational coupling. In the sense, we have take some inspiration of the Brans-Dicke theory and other scalar tensor theory, but Brans-Dicke theory in the Newtonian limit gives, by construction, by the way, a constant gravitational coupling. So in order to have a system that can be applied to cosmological context and the matter dominate, and also for example, for stars, we have found that this can be obtained through this Lagrangian here, where again it appears the gravitational coupling, but here appears also sigma, and sigma gives the variation of gravitational coupling. And we introduce here parameter, free parameter, dimensionless free parameter omega, somehow inspired by the Brans-Dicke theory, but also in this construction is allowed to have this. And you see here that G0 that can take from some reference value of gravitational coupling appears multiplied by sigma, of course by rho also, and the potential, gravitational potential, as usual in the Newtonian theory. But there is this field sigma now that accounts for the variation of gravitational coupling. So let's exploit a little this. First of all, the equations by using the Euler-Lagrange equation obtain just two couple equations here. And the variables here are essentially the gravitational potential phi and the sigma, the field that represents the variation of gravitational coupling. Of course, we must have also the continuity equation, and this, we do not touch on this conservation law, okay? We keep it as a Newtonian theory. So you can solve this equation in some context. Let's consider, for example, how we can construct a cosmology with this Newtonian theory with variable G. So Newtonian cosmology, we are going to suppose that the universe is homogeneous and isotropic. So every variation, every dependence on the here, for example, on the spatial coordinates, we drop out. Okay, and the equation simplify in this way. This equation is quite complicated to solve, but we can find some power law solution just to inspect for the first time how to implement this in the consequence. So you suppose the scalar factor. Suppose again the Hubble, the implementation of Hubble lemmatric law and the other hypotheses we have made in the pure Newtonian context. So we suppose a power law for the scalar factor and for the functions sigma that represents this variation of gravitational coupling. So we find here generalized freedom equation, and we can solve it. Not very difficult, very simple, and we obtain here the power of the scalar factor air scales like that. It has this value in terms of omega. And we see that's something I have not mentioned before, that when omega goes to plus or minus infinity, we recover the usual Newtonian theory, like in Brans-Dicke theory. Okay, this is an important point. It means that it is necessary not only to impose that sigma is constant, that is gravitational coupling is constant, but also suppose omega goes to infinity. And we can, the expression is a little complicated, but we can plot how this powers R and S varies with omega. So in abscissa here we have omega, and at left the exponent R, and at the right the exponent S. And we see the following. When S is positive, it means the gravitational coupling grows with time. We have an accelerated universe. There's something that does not appear in Newtonian cosmology, usual Newtonian cosmology, due to the attractive character of gravity in this context. But the variation of G here allows this possibility. And also, when S is negative, see here, I hope you see my indication here. So the gravitational coupling decreases with time. We have that the universe evolves in a decelerated expansion. Okay, so there are some typical relativistic effects that can be reproduced here in the Newtonian context only due to the variation of gravitational coupling. But now we would like to go a little more, see that we can make many connections here, for example, for the energy conditions, but I will not make the discussion here because of the time that is very short. So, but we can verify this quite clear from this graphic. Okay. There are other possibilities here that are not discussed, but essentially the same results. Always we have a growing gravitational coupling, we have an accelerated universe. Always we have a decrease in gravitational coupling, we have a decelerated universe. But now let us go to another context, to the problem of a star. And in Newtonian gravity, this is described by Lanianda equation. Okay, that's very well known. It's just the equilibrium condition for a sphere, okay, with a density, a pressure, and with a fluid with a given equation of state that we can study the conditions for the equilibrium. This is very well known. And the Lanianda equation is just some manipulation of Newtonian's equation in order to have some dimensionless functions and a specific condition on the equation of state. It means a polytropic equation of state that generally can be written like equation 26 that relate the pressure with the density with some constant, dimensional constant. And N is the polytropic index that is related with the thermodynamics of the system. Okay, this will give some result, for example, for white dwarfs or even for a structure like the sun. It's difficult to implement somehow the neutron stars because it's already in a relativist domain. But we can apply to the equations we have there. And now we have some relations, for example, applying for the equation for the potential, we have the relation 27. Okay, but this is made in Newtonian context. But now in our in our varying gravitational coupling context, we have these two coupled systems. It's a little more complicated now than the cosmological case, of course, because we have less symmetry. And but it's possible to verify also that we can recover the Newtonian situation when we have omega goes to infinity and sigma goes, becomes a constant. This is necessary also. Remember again, omega goes to infinity, okay? So we are going to suppose this relation for following the procedure to have the Lambda equation for the density in terms of this dimensionless quantity, theta, in the central density that plays an important, of course, a crucial role in determining the possible stellar configurations. Okay, so you have some condition, for example, theta at the origin is equal 1. It, of course, comes from here because rho c is the central density, and the area equals 0 is the center of the system. So we can write this way the gravitational potential in this way here, okay, where appears a constant, a phi constant that can place, it plays an important role because the conditions to have invariance of the redefinition of the potential here are more subtle than in the usual Newtonian context. And this constant CR must be fixed at infinity when we cover, in principle, the gravitational coupling, our usual gravitational coupling, 6.67 times 10 minus 11, okay, SE conditions. So we have this equation. These are the new Lambda equations, if you can call it this. The first one is if you fix sigma is equal 1, it's the usual Lambda equation. But due to the variation of the gravitational coupling, we have another condition that this one. And here you have again a constant lambda 0 that we can fix equal 0 if you want, okay? And we can now start the configurations, okay? And all the equations as in Lambda situation as usual, okay? It's a dimensionless equation, so we can restore the physical dimensional quantities, for example, the radius, by this relation 34. So x1 is the dimensionless radius of the star, for example, and R0 is just a constant constructed from the other constant dimensional constant that appears in the theory. So the condition to have stars is the same as usual. It means since theta is related to the density, the radius of the stars is fixed by when theta is equal 0. And we define the mass as usual also. So you have this relation for the mass. In the sense, we can have given equation of state, the radius and the mass of the system. And now we must match this interior solution with exterior solution. And the exterior solution, for example, for sigma, okay, the gravitational potential follows the usual Newtonian theory, Newtonian result, but the gravitational coupling now behaves like that, where sigma 1, sigma 2 are constants, but remark that x is the distance, so at infinity, the gravitational coupling becomes constant. Again, we have a fixed value that we identify with our laboratory value for gravitational coupling. So we can develop the conditions for the matching of the solutions inside and outside, and this allows us to have a complete scenario to determine the equilibrium of the stars. Okay, I'm running out of time if I know very well. So what we have, okay, here we plot as function of omega, again, the central value of sigma, okay, fixing the gravitational coupling at infinity. In his you can see that the values here, the value 1 is the relative, the usual Newtonian value. So for omega negative, the central value of sigma is smaller than the Newton case, but for omega positive is bigger. Okay, and you can see, for example, the result for Chandrasekhar's mass for white dwarf, and this result is the following. We see that for omega negative, since the central value of the gravitational coupling is smaller, we have a bigger increase in the Chandrasekhar limit. Okay, and for omega positive, since the central value of sigma is bigger than the Newtonian, usual Newtonian theory, we have a Chandrasekhar mass that is smaller than the the usual one obtained by using constant gravitational coupling. This is important because there are some claims now in literature that some White-Jeffrey with values of mass bigger than the Chandrasekhar limit has been detected. This is not very sure yet, but there are some discussion. But we can see that in this context, we can have a White-Jeffrey with mass greater than that fixed by the Chandrasekhar limit in when the gravitational constant is constant, really. Gravitational
Júlio, you have 3
coupling.
minutes.
Okay, so we finish. So I just say that we verify two equation of states, one is whole square that can modelize the sun in a very crude way, and we have obtained that with the density and the pressure in this in the center of the sun, we well know, we obtain very good values. A configuration that looks very similar to the sun, really, with the radius written 8 meters uh, and the mass very also similar, but with a very small variation of the gravitational coupling. That's important also because a variation of gravitational coupling can change a lot the configuration of the sun, and this will be bad for this theory. On the other hand, if you go to a neutron stars, okay, that we have a central mass, a huge central mass, 10 to 17 kilograms meter square, and a huge pressure, we obtain an object that we have the radius of 10 kilometers, okay, and a mass compatible also with the known mass of neutron star. It's quite compatible in this way. But here, the variation of the gravitational coupling is bigger of the other with respect to the case of the configuration typical of the sun. So everything seems to be quite consistent in this theory, but we have new effects like this increase in the White-Jeffrey mass, and also some specific result in the case of a neutron stars. Okay, we have some other case here for the equation of state P whole 4-3. That's quite important. Okay, and I not discuss very much this, but we have the graphic here, and again for negative omega we have a profile smaller than the Newtonian situation. That's constant one here, and the positive omega gravitational coupling that decreases. Okay, and here you have the density profile, the change for the different values of omega compared with the Newtonian case that is indicated here. So this variation allows a very many other situations that perhaps can have many applications now in astrophysics. So just going to conclusion, okay, just to say that the variability of fundamental constant is in order of the day. There is many considerations on this possibility. It's very old, it's come from Jirke, but perhaps even before, okay. But we have constructed here Newtonian theory of a variable G that's self-consistent in opposition to that formulated by Mike Witt. But we have remarked that it's not simple to construct this Newtonian theory. It's very surprising to give a Lagrange formulation. So there are some features that evokes the relativistic theory in this Newtonian theory with a variety. This is very interesting for reasons discussed before, because we have neutron star configuration that allows for different mass, and there's this question that there are some neutron stars, at least they are in discussion in the literature with a mass bigger than the supposed in the beginning. This is allowed in this theory. And also there are other 2 points that must be stressed. Why to construct this? Of course, from an academic point of view, we can do it, but first it can make a reverse situation. It means it can inspire some formulation of scalar tensor theory in the relativistic regime outside the, for example, the Rondesk context. This may be something we want to investigate. And also 2 more practical applications of this. For example, for numerical simulations, if you want to make numerical simulations of theory of RNG, it's not simple, but because in numerical simulation, we use a Newtonian theory, but with a constant gravitational coupling, here we can allow this variation. And this may have some implication, also to study some specific astrophysical system. We have talked about white dwarfs and neutron star, but you can think in other contexts, for example, cluster of galaxies. This I think that we are studying now. So just one word at the end that this work we began in discussion a long time ago with Professor Brazil, that was my advisor during the beginning of my career, that founder of our group, research group here in Espírito Santo, and who has died last year, 1.5 years ago. So just as an honor also to offer that, like very much some Newtonian formulations, I'd like to also to make this honor to Brazil, that was also discussed a long time ago. We began, but unfortunately at the time before his death, we have not closed this analysis. So thank you very much.
Okay, Júlio, thank you very much. We have time for a couple of questions before the next talk. Please, Marcelo.
Júlio, I have a question. So why it is important to do everything in Newtonian cosmology? Why you cannot do it relativistic?
Well, yeah, there are some points. First, numerical simulation, to my knowledge, almost all the time use a Newtonian structure equations, okay? So if you want to implement some variation of gravitational coupling, like in Brzezinski theory and numerical simulation, of course you can do it, but you must make some considerations that it's not so direct, okay? So it will have some, to my point of view, many applications to this case. Second, some kind of star, white dwarfs, for example, okay? They are Newtonian regime. Quantum mechanics is very important to understand white dwarfs, but we use essentially Newtonian theory, okay? We can correct with using relativistic, but we are still in the Newtonian regime. So as we have seen here, when you use, we can implement in this case the variation of G. And when we implement this, we can see that the effects of variation of G are very clear, okay? Because we change the mass according to the free parameter omega in a sensible way. For example, this is a little more complicated as far as I know in the Brzezinski theory, because in Brzezinski theory, the Newtonian limit gives G constant. If the relativistic theory is suppose that the gravitational coupling change with time. So I think, and we have verified in Mann's case, that we can have quite clear results due to this variation of G. In systems that we can apply the Newtonian regime. The neutron star is more complicated. They are already in relativistic, but you can reproduce many relativistic effects using this theory, as we have described.
Okay, thank you.
Thank you, Marcelo. Okay. Please, Marcelo Rebouças, you raised your hand.
Okay, fine, thanks. Júlio, just some, I'd like to hear you about some points that relate to the first question. when I look at theories, I remember that the vacuum theories in GR are very important. Among the vacuum theories, we've got black holes, and we've got gravitational waves. And my first question, I've got two questions. My first question is, as far as I could understand, you deal with a theory that you change the gravitational constant. You mentioned the acceleration of the universe, which is a cosmological issue. But you didn't mention what to me it's crucial nowadays is gravitational waves.
Yeah.
Do you have something to say about this in this context of this theory? What did it tell you as something else about
yes,
gravitational wave?
Yes, okay, the question is the following. The equations, if you look at the equations, if you see the coupled equations, you see that it's quite possible, this is the complete equations, okay? It's quite possible that we have gravitational waves here. We have begun to analyze this problem in the vacuum situation. Even look at the vacuum, it's not very difficult because the way the equation appear, it's quite strange. But strange, no, it's somehow complicated. By the way, this is one of the point. We hope at the beginning, when discussed with Brazil a long time ago, that we should have some very simple equation, very simple Lagrangian. It's not the case. Not that you have something that, if you want just to treat cosmology, you can have something simple. You want just treat stars, static situation like stars, it's simple. But the complete, something that covers the two domains, not so simple. And at our investigation, we are now analyzing this. The first point is that, in principle, we can have waves here, okay, that can assure we can connect with gravitational waves. But there are some points that is not for us. You make some, let's say, we use the jargon, work in progress, okay? That here the symmetries are a little complicated because a wave must be invariant by the Lorentz transformation. You don't have a Lagrangian, a Newtonian theory, so it's Galileo transformation that applies here. But we have found at least some equations that seems that we have some ways connected with the function sigma that relate to the gravitational coupling. But strangely do not have in principle something very clear on the potential. So it's connected, to my point of view, with the problem of the symmetry of this equation. They are invariant by Galileo, even though it seems they contain some types of wave, and we are analyzing this now. For first moment, I was very happy that I have found a wave really, even for psi, but I have made a mistake, so I have to correct them. And the situation is a little more complicated, not exactly a mistake. Sometimes I have tried to circumvent this problem of the group invariance, Lorentz, how to somehow to obtain a Lorentz invariance. It depends on the observer, and there are other points that in this equation that seems quite curious. For example, the gravitational potential is not like in Newtonian theory, in opposition, let's say, to Newtonian theory, invariant by a rigid transformation of the potential plus a constant. It's more complicated here. So it seems we have gravitation, some types of waves. We are now investigate which kind of waves exactly we have.
Because this is crucial. A lot of theories have just been ruled out just because the detection of gravitational wave velocity. So you have to confront with this and the polarization of gravitational wave of the recent experiment. That's my motivation. Otherwise, we're in the generate new theory for what?
But just a remark, Marcel, we do not pretend. that this theory, it's a fine word, it's not relativistic. It must be encoded in a relativistic domain. But one of the problems, which relativistic theory will contain this theory as limit? It's not very clear.
This is a good question. GR doesn't seem to be the case.
No, neither Brunswick, neither Hondersk. Perhaps that's what some think, that it's vague, very vague from the moment, but exactly one point we like to investigate is perhaps some more general class of theories, of scalar tensor theories, that could have these equations as limit. Perhaps not high derivative graph. It's not very clear, but we hope to construct this. We are not, but we are touching, because it's a reverse problem. In general, you formulate a relativistic one and have the Newtonian limit. Here you have a Newtonian theory, and which is the relativistic theory that corresponds to this Newtonian limit. We are treating this problem, but it's not very easy. Okay, like for example, the first motivation for this, and discussing in Brazil, was saying, let's look for Brunswick and try to obtain a Newtonian theory with RNG that could be more complete than the McVitie proposal. Brunswick does not give any answer to this. It gives just Newtonian theory with constancy.
Júlio, I think that we can continue this after. Okay, Professor
Yeah, thank you very much.
Okay, thank you, Júlio. So our next speaker is Professor Germán Lugones from UFABC. He will talk about phase transitions in neutron stars, implications for stellar and physical stability of gravitational waves. Where are you, Germán?
Okay, I'm here.
Okay. You can share.
See here, share screen.
Yes.
Can you see my screen now?
Yes, it's good.
Okay. Okay. Just a moment here. Okay, I will talk about neutron stars, specifically a kind of neutron stars that is known as hybrid stars. For those people that are not experts on the area, I have here a plot where I show all the theoretical possibilities for neutron star interiors. You have, of course, the common neutron star, or the traditional neutron star, made essentially by neutrons, protons, and electrons. Essentially, but you have many other possibilities. Essentially, what you have here is that the external layers of the star are reasonably well understood, but the interior region is still unknown. So I will work with the possibility of having a quark matter core at the central region of the star. This is what we know as a quark hybrid star. A very important tool for understanding the internal composition of neutron stars is the so-called mass-radius relation. Essentially, to describe the interior of the neutron star, you need an equation of state. The problem is that above a few times the nuclear saturation density, the density that you find at the interior of the atomic nucleus, you don't know the equation of state because you don't have experiments, and the theory is very difficult to solve. So essentially, you have a lot of equations of states that are extrapolations of what we know at low densities. And in this regime, astrophysics is very important because we can use astrophysical observations to put constraints on the behavior of matter at the microscopic level. So you can, one tool, a very important tool, is the mass radius relation. It's not the only one, but essentially the idea is that for each equation of state, you can derive a theoretical curve for the mass and the radius of the star. Each point here is represents a star that has a given mass and a given radius. Each curve here corresponds to a different equation of state on the left, and in such a way, making observations on the mass and on the radius of neutron stars, you can say something about the microscopic behavior of matter. This is not the only tool. With the beginning of observations of gravitational waves, there are other tools, very interesting, that I will mention later in this talk, such as the comparison of our equation of state with the tidal deformation of stars in the binary systems and the detection of pulsations of gravitational waves from pulsations of neutron stars. I here summarized some few observations that are very important for knowing the interior of neutron stars. There are the most precise measurements of neutron star masses come from binary systems. But the important point here is that since 2010, people have discovered some neutron stars with about 2 solar masses. These are unexpectedly high masses for neutron stars. Before that time, people didn't believe that such high masses could be possible. These are very good measurements with a very small error. And this puts a strong constraint on the equation of state, because it means that any model for the equation of state must be able to produce at least stellar configurations with 2 solar masses. Then since 2017, we have a very important mass and radius determination from the Neutron Star Interior Composition Explorer, which is NICER, which is a mission in the International Space Station dedicated exclusively to the analysis of neutron stars. And using this technique, the pulse profile model of hotspots in the neutron star surface, they have determined the mass and the radius of 2 objects with very high precision. The interesting point here is that this object has 1.4 solar masses. This other one has 2 solar masses, but both of them have very similar radii, around 13 kilometers. So this means that the mass-radius relationship I showed before is quite vertical here. So this gives information about the stiffness of the equation of state, and it seems to favor stiff equation of state for matter at high densities. And finally, we have since 2017 the first detection of a binary neutron star system by the LIGO and Virgo. Since then, we have another candidates. Apparently, all of them involve a neutron star and a black hole. So the most important one is this, because it has more data. Tidal deformation has been measured. The chirp mass has been well constrained. We have also electromagnetic counterparts from X-rays to gamma rays. So this allows to put stringent limits on the mass and radius of the objects that participated in this merging. Okay, now let me say something about the equation of state of dense matter. I have made here a separation of the equation of state into 2 regimes. What I call the low density regime is the one that represents the outer crust and the inner crust of the star here and part of the outer core. And it's a density regime where the equation of state is reasonably well understood. There are ways of describe systematically the nuclear force up to densities around between 1 and 2 times the nuclear saturation density. But beyond that value, the interactions derived from this chiral effective field theory are uncertain. So the equation of state is not reliable anymore. So we enter at higher densities the regime where we have to work with extrapolations. Essentially, you have two types of extrapolations. One is an extrapolation made on phenomenological nuclear interactions. You construct a Lagrangian or a Hamiltonian that represents what you expect from the behavior of matter at high densities, and try to adjust and to match this with experiments at low densities. And there are other approach, which is a model agnostic approach, where you use different basis functions, for example, piecewise polytopes, fulfilling causality, and trying to use constraints from astrophysics in order to delimit the region where the equation of state can be. Then we have at asymptotically large densities, which are densities much higher than the central density of a neutron star. Here at the center, you normally expect something between 3 to 9 times the nuclear saturation density. So at densities of around 40 and 50 times the nuclear saturation densities, you can do perturbative quantum chromodynamics. So there are calculations in this regime, and you can derive some limits to the equation of state. So essentially, we can summarize what we know about the equation of state of dense matter in this plot. You have here limits coming from a low density nuclear theory. Here, limits coming from perturbative QCD at high densities. And in the middle, you have a region that is still unknown, but can be restricted using astrophysical observations. Neutron stars are in this regime, more or less. So essentially, you don't expect that neutron star will fall in this part of the equation of state. Okay, in this work, I will work with the hypothesis that quark matter exists at the center of neutron stars. So I will assume that in the low density regime, we have hadronic matter. I will use equations of state a large set of equations of state that match these limits coming from theory and experiments. And I will assume that there is a phase transition, a sharp first order phase transition at some point. This will be treated as a free parameter. The pressure and the density shunt here are free parameters in our model. And then at high densities, we have quark matter that matches the perturbative QCD at very high densities. Okay, let me say something about stellar stability of stars without phase transition. So these are one-phase stars without quark matter in the center. These results are very well-known results, are textbook results, but it's important to summarize them because I will show them how these theorems change when you include density discontinuities inside the star. So if you want to know that whether the stellar configuration is stable or unstable under small perturbations, you do the stability analysis introduced by Chandrasekhar in the 60s. The idea is that you construct an equilibrium model, then you introduce first order rate perturbations in the metric and in the thermodynamic variables around the equilibrium configuration. You assume that perturbations have a time dependence, harmonic time dependence, where omega is a characteristic frequency to be determined. You impose value number conservation. Then you put all this in the Einstein equations, and you derive the form of the Einstein equation that has the form of a Sturm-Liouville problem for the fluid Lagrangian displacement, C, which is the displacement of each fluid element around its equilibrium position, and the Lagrangian perturbation in the pressure, which is the pressure change around the equilibrium pressure. This system of equations verify the boundary conditions only for discrete values of the frequency, which are the quasi-normal modes of oscillation, or the normal modes of oscillations of the star. So these are the frequencies that verify this equation. Since this is a Sturm-Liouville problem, there is a theorem that says that eigenfrequencies are ordered. So the fundamental, there is a fundamental mode which is smaller than all the other ones. Then as a consequence, we can say that the fundamental frequency is the one that determines stellar stability. So the standard result is summarized here. If you have a fundamental frequency whose square is positive for a given star, this means that all other frequencies are real, and any perturbation of the star will oscillate in this way, will have a harmonic motion, and the star is stable. If this value is negative for a given star, the frequency is purely imaginary, so the amplitude of the perturbation will grow exponentially and the star is unstable. So this is the standard analysis for Chandrasekhar. Also in the 60s, these people, Harrison, Thorne, Wakano, and Wheeler, derived an equivalent stability criterion, which is static. It doesn't need the solution of the perturbation equations, although it is restricted to some specific cases. So they consider a specific kind or specific type of equation of state, which are cold catalyzed equations of state, which means that matter is cold, it's at 0 temperature, and it is in chemical equilibrium. And they assume also that the equation of state is continuous, it has no discontinuities. Then, with this hypothesis, they arrive to the conclusion that if all frequencies are real, that is, if the star is stable, then the derivative of the mass of the star with respect to the central density is positive. And if the star is unstable, then this means, on the contrary, in fact, if the derivative is negative, it means that the frequency is imaginary, so the system is unstable. So this analysis led us to the very well-known result that you have this branch of stable configurations, which are white dwarfs, where the mass is an increasing function of the central density. Then you have a branch here that is unstable. At this region, at the minimum, you recover stability and you have neutron stars until the maximum here, where stellar configurations are unstable again. So changes of stability occur at stationary points, maxima and minima. This condition can be extended to a diagram of the mass versus the radius, and you also see that the changes of stability occur at maxima here and minima, and here again. Okay, so what happens when the hypothesis of this theorem are not fulfilled, which is the case of hybrid stars having quark matter in the center? We analyzed this in a work, in a recent work. The idea is that you have in the central region of the star, you have quark matter. In the mantle, you have hadronic matter, and you have a discontinuity between both. The question here is what happens if the equation of state has a density jump and you perturb this system, you introduce perturbations in this system. When you introduce a perturbation, fluid elements move around their equilibrium position. So they go back and forth doing this movement. So the situation is the following. What happens if this fluid element moves here to a region where the density is smaller? We are around the transition density. So we would expect that this element moves to the right and the density is smaller there. So it would convert into hadrons and then it would go back and convert into quarks. But the situation is not so simple. It depends on the time scale of the reactions that convert one phase into the other with respect to the time scale of the perturbation, that is the period of the perturbation. So if you have that the reaction time scale is much smaller than the period of perturbations, this means that reactions are almost instantaneous. And when the fluid element moves to the right, it converts, and when it moves to the left, it converts again. So there is an instantaneous change of the nature of the volume elements near the interface, and the interface stays at the same place always. But you may also consider a possibility where the reactions are slow, so there is no time for conversions to act or to occur when the fluid elements move to the region with a smaller density. So in this case, the fluid element will go back to the original position here before having any conversion. So this is the case of that we call slow conversions. The time scale of reactions is much larger than the period of oscillations. Here, we know that the period of oscillations is around 1 millisecond in neutron stars, or 0.1 milliseconds. So reactions are slow or rapid with respect to this value, 1 millisecond per minute. So to analyze this problem, the important point is that in spite of the conversion process being very complex, the fact that this, in the case of rapid reactions, the interface stays at the same place, and in the case of slow reactions, it moves with the same period of oscillations, makes possible to implement this reaction speed as simple junction conditions in the Chandrasekhar equations. So this is what we did in this paper. And we analyzed the stability using the Chandrasekhar equations for the specific case of slow reactions and rapid reactions. The results are the following. We found that for rapid transitions, we find the same behavior as for one-phase stars. So the standard stability criterion, static stability criterion, is valid. So you can look at changes of stability at the maxima and minima of the mass radius relationship. But when slow transitions are occurring at the interface, we find that changes of stability do not occur at stationary points, and the static criterion is no longer valid. So essentially, the result is summarized in this schematic plot. If reactions are rapid, you have, for example, here in the mass and radius relation, a stable hadronic branch. Here you have the onset of the quark transition. So we have a quark matter core here, a small quark matter core, but the curve is to the left of the maximum. So this region is unstable for rapid conversions. But if you analyze with the same equation of states the problem, but now considering that conversions are slow, you find that this branch is stable in spite of being beyond the maximum. So this is a new branch of stable neutron stars, in fact hybrid stars, that we call slow stable hybrid stars. This is not the only possibility. This is a new branch that happens at high masses and high densities, but you find this also at low densities and low masses. This, for example, for rapid conversions, this small segment is unstable, but for slow conversions, this is dynamically stable. Okay, let me show some results using specific equations of states. Here we have analyzed this for state-of-the-art equations of state for hadronic matter and quark matter, and the results show that for a wide range of the equation parameters, of the equations of state, we always find that the new branch, which is here, is very long. So it goes from more than 2 solar masses here to less than 1.5 solar masses here. So this is the hadronic branch here, and this is the new branch for many cases. All astrophysical constraints are fulfilled. For example, the 2 solar mass pulsars are here. The LIGO Virgo detection of GW170817 is here. The NICER pulsars are here also, and you can fulfill this using a stiff hadronic equation of state for reproducing NICER and 2 some neutron stars. And this new branch explains GW170817 as well as this very large mass pulsars. Another interesting result is that we find twin stars. Twin stars are stars that have the same mass. For example, this one with this one of the same curve here have the same mass but different radii. So this is a way of identifying the possible existence of this hypothetical new branch of stars. And another interesting result is that we find that in this region here, very high densities are possible at the center of these stars. We find that the central density is several tens of times the nuclear saturation density. Now we have also calculated the tidal deformability as a function of the mass.
Germán, 2 minutes, please.
Okay,
2 minutes.
Here we find that 2 minutes. Okay, here we find that the tidal deformability of this new branch is much smaller than the tidal deformability of hybrid stars. Here we have calculated the tidal deformability for binary neutron star systems, assuming or considering the same chip mass and mass ratio as this event. So we find here this is our systems with 2 hadronic stars. These are systems with 2 slow stable hybrid stars, and this one and this one are systems with 1 slow stable hybrid star and a hadronic star. And we see that in all cases, the results for including this new branch of stars fall inside the 19 or the 50 confidence interval for this object, GW170817. And finally, I will briefly comment another way of discriminating this new kind of stars from standard hybrid stars, which are G modes. G modes are non-radial oscillation modes that occur when you have a discontinuity in the star that is oscillating, and you have a quasi-normal mode associated with buoyancy of elements that move around the interface. These are called gravity modes. We have calculated the frequencies and the damping times due to gravitational wave emission of these modes. And we find that for standard hybrid stars with that are stable under rapid or small or slow reactions, the frequencies are here and the damping times are here. So they have frequencies of small frequencies and very long damping times. But in the case of this new branch of hybrid stars, the frequencies are significantly larger and they have much shorter damping times here. So it is possible to discriminate both kinds of stars and say something about the reaction speed between quarks and hadrons by looking at these non-radial oscillation modes. So here is the summary of my talk. We demonstrate that a new branch of hybrid stars is possible if interface conversions at hybrid stars are slow. This fulfills all current observational constraints. if this is the case in nature, we very extremely high densities could be possible at the center of these objects. And we have some ways to identify observationally these objects. One is by looking for twin stars having the same mass but different radii, or the other one is by looking at GMOs using gravitational wave detectors, and the other one is by looking for small tidal deformabilities in binary mergers of neutron stars. That's all. Thank you very much.
Okay, Professor Germán, thank you. So we can start questions first for Professor Germán, and then we can go to the other seminars. Let me see. Someone is, I can see who.
Alex.
Alex. Okay, please. Can I see?
Okay, can you hear me well?
Yes.
Yes.
Okay, hello, Germán. Long time no see you.
Hello, how are you?
Good. So it's a quick question regarding this phase transition from one state to another state in the hybrid stars. Do you think this event can be short enough that it might be able to explain fast radio bursts somehow, the no-repeater fast radio bursts? Do you have a
so
view on
can
this?
you repeat, because the audio is not very good. Can you repeat?
Yes, let me see. Okay. Do you think that the transition between the stages of the hybrid stars can be fast enough that it might explain a no-repeater fast radio burst?
I don't think so, because the amount of matter involved in this conversion is very small. So to explain a repeater, you need a lot of energy. And this is a very thin layer of the star that is oscillating and eventually converting. So I think it's not possible, except if you have a very large amplitude oscillation in such a way to involve a large amounts of matter oscillating. But in this case, you have to go to the nonlinear regime, and we cannot guarantee that the system will be stable.
Okay, even for a single event, you think it would not be possible? Just
For a
one
single event, probably yes. For a single event, probably yes. But you need a very large excitation of the system in order to the surface will move several hundreds of meters or more, and converting hadronic matter into quark matter. But I don't know what would happen then, because if the perturbation is large enough, the system can become unstable. Even a system that is stable under small perturbations will not be necessarily stable when you move large amounts of matter.
Okay, thanks.
Okay, Rogério, you have a question?
Hello, Germán. How are you?
Hello.
Long time don't see also. So I just want to understand a little better. So you found another branch, which is due to this slow stable hybrid stars. So this low interface conversion. So my question is, what is the physics that is different in this slow interface conversions with respect to usual interface conversions? What is the new physics?
Okay, the physics is very complex, so because of this reason I didn't comment about this, but it is a very interesting question. The idea is that you have the interface, but when you move from one side to the other of the conversion has an activation barrier. So the equilibrium the chemical equilibrium of hadronic of quarks inside hadrons is different from the chemical equilibrium of quarks that are free. So it is not simply that you take matter here, you deconfine, and they are automatically into equilibrium. There is, if you deconfine matter on the hadronic side, you will have free quarks that are not in chemical equilibrium. So this has a larger free energy than the preferred state of matter on the other side. So this introduces an activation barrier for the conversion. And so the problem is not simple direct deconfinement, but the nucleation process. And in the nucleation process, you have very many other ingredients such as surface tension of the drop. You have Coulomb effects, and you have many other things. So when you, of course, in this density regime, you cannot calculate this from first principles, but there are model calculations, model dependent calculations. And when you do these model dependent calculations, you find that the nucleation timescale is large. It's very large. It's more than years. So this means that the matter can go to the other side, and it needs at least 1 or more years to nucleate on the other side. So in this sense, this model dependent calculations show that they are slow, but they are model dependent. So we cannot say, okay, they are slow.
Yeah.
This is the physical, microphysical motivation of studying this.
Thanks. It's clear now, and I think these nucleation rates are very sensitive because it's barrier penetration is exponential. They're always exponential.
When
So
you plot the
yeah.
nucleation time, it's almost vertical with the so you change the parameters very little, and you have many orders of magnitude of change in the nucleation time.
Yeah. So I can see the origin of the problem. Thank you, Germán.
More questions? So I think that we can open for the other speakers. Okay. I would like to ask Júlio. I'm interested about the experimental evidences of G, variable G, possible, I don't know, future evidences, if you can tell me.
For the variation of G?
Yeah.
Well, I think that objects like sun, that's one point, and then I think that they can have little space to a huge variation of G across all the radius, no? And for example, on opposition, the case of neutron stars that Germán Lugones has described as interesting objects, situation. I think there it's possible to due to the strong gravitational regime to have a more detectable variation of G. There is a problem testing this kind of object like neutron stars because there is a degeneracy. As Germán has described somehow, since the equation of state is not known in details, there are some structures that the composition even of the neutron stars. But in this strong regime, I think it is possible to detect some variation. But the problem is the degeneracy with other parameters in this case. And also, I think in some, for example, in the primordial cosmology. So in strong situations, mainly, of the gravitational field. The test that has been made, for example, equilibrium stars gives a constraint, a very huge constraint, but they have been applied mainly to stars that are deep in the Newtonian regime. So, and the star that does not present, for example, the sun. So I think that the space to detect this variation could come exactly from these objects, mainly. For example, in the Earth, unless some experiments you can think on some experiment. I think it's almost constant. There is not possible. That's why, by the way, that our results indicate that an object with the sun, for example, stars in this way, this type, there is the variation. If it allow the variation is very small. Okay, but in compact objects, no. But there it appears this problem of degeneracy. In any case, the neutron stars, for any modified theory of gravity, there is this problem. If you try to apply Hondersky or other generalization of the gravity theory, you have this problem because you do not know the equation of state. So you must wait a little.
Okay.
But for example, what was a good result was white dwarfs. In this, we can see a change in the Chandrasekhar limit that can be detectable. And there is some results recently that indicate some anomalous object that seems to be white dwarfs. So perhaps we have space for that. I do not know if I answer your question with this.
Yes, no, it's very interesting. Thank you. Rogério, you raised your hand.
Yeah, so my question is also for Júlio and for Ilya, because Júlio, you know that in Ilya's talk, he can have a variation of G. Actually, he has an equation variation of G. So you don't have to look further. It's already there. So maybe maybe you can use Ilya's variation of G to put in your put constraints also. That could be interesting.
Of course. G and lambda.
G and lambda, yeah.
The point is that is a relativistic theory.
Yeah, but they can take the non-relativistic limits.
With quantum effects. So what we our aim, Rogério, was quite simple in some sense. It was to try to obtain a Newtonian theory, the low gravitational regimes, small gravitational regimes that could implement this idea of variation of G. I think that even the case of Ilya, if you go to Newtonian limit, you must find something constant. That's the point.
Ask him.
Yes. I have not verified, but I think some variations. As far as I know, all system, all modified gravity theory, even in quantum regime, is coming from the quantum regime we have investigated. When you go to the Newtonian limit to obtain G constant. Brzezinski theory is the most obvious, but the other ones, Rondeska, for example.
Yeah, well, Ilya is here, so he can answer, but Marcelo has a question.
I don't know. We actually in the semi-classical models, Júlio made very important contribution, and here it is new, so we can discuss it, but I don't know what it will give. So probably it will have some, like, for density perturbations will be the same as relativistic theory or close, at least in the matter-dominated epoch. But in the matter-dominated epoch, these models are not very, typically they don't give big difference. Like in our last paper with Júlio, two papers actually, we found that and explained actually that these models become very interesting in the early universe. Mm-hmm. When you have strong background, you can create particles. Mm-hmm. And with this, I don't know. Maybe it will be like one more constraint on this running, because there are some ambiguities behind it. But in this form, which I showed today, no. So, but this can be like close the model, which is always good.
Mm-hmm. Perhaps, yeah. Perhaps the problem of compact stars, compact stellar objects, could be interesting to test also.
Sure. The difference with the previous case is that this we can calculate. Mm-hmm. Okay.
Okay, Marcelo. Go ahead, Marcelo. I can hear you. Your phone, Marcel, please.
Oh, sorry for that.
Okay, Bill.
For Martin, one question that occurs to me is that that was the beginning of the test of GR, was the band of lights. And now you've come to the same question, use lens, and you gave a nice seminar, but it wasn't clear to me why you choose low redshift.
Right. So actually, I mean, first, the tests of general relativity of gamma, which are strong, are at small distances, right? So if we think that there is some theory of modified gravity, this gamma would be a variable, right? And at some scale, we approximate it by a constant. And the limits on this constant at kiloparsec scales are not super stringent. Actually, if you look at limits on gamma as a function of the scale, the limits get bad as the scale gets larger, right? So for smaller scales, there are more stringent limits on gamma. Don't look specifically at small scale, I mean, at short distances. We are interested in lenses that span a wide redshift interval, because what we are probing is gamma close to the lens, right? That's where the bending of light occurs. So regardless of the redshift of the lens, we are probing gamma at this redshift. So we really would like to have a big range of redshifts. So they're probing gamma in different cosmic times, right? I don't know if this answers your question.
That's a very nice point. Well, good.
Thanks.
Thanks a lot.
Okay, more questions?
I've got one to Maha. He is not here, I think. So no, there is no sense to ask him.
He is not. Okay.
And what's a comment to Marcus Maya talk? I didn't quite get where he intends to use the modification and the quantum graph approach if it's not in sub-Planckian scale. I mean, nowadays we don't see any sign of quantum graphs around us in the astronomy, in cosmology, apart from primordial universe, or in very high condensed matter in the universe. So I got the feeling that is so classical, the approach, and I could not see where that could be somehow used as a quantum graphs approach to some phenomena.
Okay, finished. You see, I was explaining to you before that not using the Planck scale.
Yeah, I see. I saw that. That's why I am complaining.
But Planck scale is something calculated with G. If you don't have G, then Planck scale is just a fantasy. There is nothing real about it. It's not a fantasy. The Planck scale is, I mean, the gravitational constant that we know today was calculated from Newtonian gravitation in the 18th to 17th century. And this is just ordinary matter made of atoms. So if we look at now the data from the Planck satellite, the cosmic microwave background radiation,
from the very early universe,
the ordinary matter is only 4.5% of the universe. So we are very ignorant about, this is the size of our ignorance about the universe. Only 4.5%. if you want to construct a theory of gravity, that applies to the 95%, we have to change the gravitational constant.
I thought you was speaking about quantum gravity. And my
Yes.
point is that it's only had sense in that period of the universe. As for example, primordial universal in very high gravitational fields, say, objects.
Yeah, I was talking
That
about,
I don't see, I mean, I don't see where you can use quantum gravity.
no, quantum gravity is the origin of the gravity, I suppose. If it is, gravity is a fundamental interaction, and we believe it is, then it should have been put together with the gauge theory to form a real standard model of interactions. The trouble is, G was borrowed by Einstein from Newtonian mechanics. And now you see the limits of the Newtonian theory was determined by Mostepanenko, by the Vladimir Mostepanenko and Galina Mostepanenko. They found that in the small scale, G, or Newtonian gravity, measuring by torsion balance, is only 4 microns, 10 to the minus 4 distance. Beyond that, nobody can assert anything. And for the large scale, it's about the diameter of our galaxy, because the rotation curves of the stars in the outer arms of these spiral galaxies is not, I mean, if you count only ordinary matter forming the stars, it doesn't go beyond that. Even the stars in the outmost arms of our galaxy are speeding up more than 700,000 kilometers per second. And this is beyond the measure. We need dark matter to explain the existing galaxy. So this is because it's using G as the standard measure of gravitation. If you go now for quantum gravity, then you have other things, the quantum black holes, this thing that Hawking was talking about, and also the spin 2 fields that also produce gravitation, as I showed you in the transparencies. So it's necessary to have quantized gravitation to have a good model of the universe.
Yeah, I'm not against. I'm just trying to find out where your approach could be used in practice. But you mentioned one situation now, it's clear to me, when you go beyond, when you go smaller to smaller, say, length scale, as you mentioned, the experiment that people measure the gravitational constant, which is the way I see. I use Planck scale.
No, this is not
on the scale that you have used on the scale that say there are some experiments. I use a Planck scale that we've got a theoretical estimation.
Everybody,
I know that they are different. There is a far gap between them still, but I see your point. I see where at least you expect that could be used. My question now that would arise from your comment is whether we still can say model the universe as a manifold with matrices, continuous matrices, and so on. It's not clear to me that, you see. But you use these say, mathematics in your formulation.
Yeah.
Okay. I think I'm happy.
Okay.
I'm happy with your comment.
Thank you. Glad to make you happy.
You're muted, Vanessa.
Sorry?
Sorry. You can make some questions in chat if you want. We have probably students here. So, Rogério, please.
Yeah, I have a question for Martin. Martin, first half of your talk, you mentioned the importance of having spectroscopic redshifts, if I remember correctly, for the characterization of the lensing. But then in the second part, it said something that was really amazing, that apparently from this machine learning exercise, the lensing redshift is not important. And this is incredible. And do you have, so I have a couple of questions. Do you have an understanding of this? First question. The second question is whether, the second question is more related to the Markov chain Monte Carlo analysis that you guys made and the nuisance parameters that you used, specifically if the redshift uncertainty is one of the nuisance parameters.
Right. Okay. So the first question, right? It's first I emphasize that you need the redshift, and then I say you don't need them. So for the standard analysis, what you do is you make the modeling of the lens distribution, and for this you need the redshifts. And usually it's supposed that you need spectroscopic redshifts of the lens and the source for the distances. But then when we look at these simulations, we see that the parameter that we want to recover, which is the velocity dispersion, which is what mostly matters, seems to be very well recovered regardless of our knowledge of the redshift. So this is something we want to explore. So the reason is not very clear now. One possibility is that, okay, we need a redshift for the modeling, but at the end, what matters is sigma v. And we could just make some very simple simulations to see how at the end, the uncertainty in the redshifts impacts sigma v, right? That's not what we usually look at. So that's something we can assess about the sensitivity of the final result to the redshift. So that's one point. And another point is that we are using the simulated data, and this is not simulations that we have run. So it could be that this tight relationship between these three quantities, the Einstein radius and the two redshifts, maybe it's embedded in the simulations because they probe a very small range of sigma v. So maybe we just recover sigma v because simulations have similar sigma v. So that's something we want to check. So yeah, but it's I mean, in any case, it's something we can address. So that's a reply we don't have, but we can have soon. Regarding your other question about what we are marginalizing in the MCMC, so no, we are fixing the redshifts, and we marginalize over beta, which is this anisotropy of the velocity dispersion constant, and we marginalize with a prior, quite strong prior, and the same for the density profile, for which we use a prior. So basically, we have these three parameters: the sleep, the anisotropy of the velocity dispersions, and the slopes of both the light profile and the mass profiles. So these are three parameters, and sigma v, of course, and we marginalize over two of them with some quite strong priors.
Thank you. Thank you, Martin. That was very clear. Thank you.
Thanks.
Okay, more questions? No questions?
So when it was live, in person was more lively. It was more,
Yeah, it's
there
better.
were more questions.
The next
There
will
were
be,
more,
please.
there were more fights before that.
It is nice to see this paredão here. It looks like more a paredão.
Paredão, exactly.
in the big screen.
We have
Well,
a
the
Yes,
fight
it looks
is-
like the Big Brother.
Big
Looks
brother.
like the Big Brother.
The fight is more interesting when you think you have the possibility of going to the hands, you know. So
Yes.
although it
That's
doesn't
right.
happen, but you know.
Or the possibility of having a beer afterwards.
Yes, I think that's more the second one. Yes. But it's very nice to see all these people here, which reminds us a lot of the original New Physics in Space meetings, right? It's very nice to see all these people, many new
Yes.
faces, but also many of the, you know, reminders of the first series of meetings. So it's good to see you all.
Hopefully you can make it back again in a personal style, because the paredão was the best idea that I've seen in many years regarding these discussions. It was awesome.
Yes, that's true.
One suggestion that even we go back to the original forms of meetings, I think we should keep this because it has a wide range of audience. Yeah, maybe people listening to us, we don't know who.
Yeah, hybrid form. Yeah. Okay, very good. So I just want to remind you that we have 7 posters for tomorrow, and they're already the files with the videos, etc., is already in the page. And yeah, and so let's have tomorrow a more lively discussion session. Okay, that's the.
Júlio, send me the list of posters.
It's on the page.
It's on the page.
On the page. There is a tab called posters.
Okay.
If you go there, there's 7 posters, and every poster has a PDF file and a video, very short video file.
Okay. Fine.
Please take a look for tomorrow, okay? And then the poster presenters will give like two minutes presentations tomorrow.
Good.
Okay.
So we have time to discussions about posters.
Yeah,
Yes.
yeah. We can discuss.
Yes.
We can discuss everything afterwards. Yes.
Okay. Very
Good.
Bye-bye.
The most important part of this is discussions. So,
Yes.
okay. So see you tomorrow. Bye bye. Thank you.
Bye bye.
Bye-bye. See you
See you tomorrow.